So one announcement: tomorrow after class, I will send you a set of quiz which will not include today's and tomorrow's class, but rest of it is included. Okay? And I will also give you some time, a timeline by which you have to submit your quiz answers. So that is going to happen tomorrow. But today's class and tomorrow's class will not be included. All right. And today we are going to discuss something very, very important. As an earth and environmental scientist, uh, this is one of the emerging areas which you should understand about. And this is all about carbon capture and storage. Okay. So I have given a link with this slide pack, which you can go to, and you can actually read a lot about carbon capture and storage. So this is your background reading, or that you can take help from. Okay? So carbon capture and storage is often also uh, acronymed as CCS. Okay? There is another new term which people use nowadays, which we call as CCUS, where this stands for carbon capture, utilization, carbon capture, utilization, and storage. So we'll discuss what is the difference between CCS and CCUS in a moment. Now let me just give you a context what CCS is all about. CCS essentially means that when you burn any sort of fossil fuel, okay, so when you burn fossil fuel, be it coal, be it oil, be it natural gas, yeah, you generate a lot of carbon dioxide, of course, right? And the adverse effect of carbon dioxide, I don't have to essentially talk you through, simply because you know what it does. It is one of the primary greenhouse gases, right? This is one of the primary greenhouse gases, and that essentially has huge impact on global warming, right? So there is a natural carbon cycle that takes place, which we talked about before. But then, while you burn fossil fuel in the industry or anywhere, the carbon dioxide that you generate is actually the surplus carbon dioxide, which is not, which doesn't get completely neutralized by the carbon cycle. So it remains kind of free in the atmosphere, which results all sorts of environmental disasters like greenhouse gas increment in the greenhouse gas content in the atmosphere, and resultant global warming, right? So carbon capture and storage is a process. Yeah, this is a process by which you capture the carbon dioxide, okay, capture the carbon dioxide from capture CO2, capture CO2 from industrial sites, and then store it in geological formations. Okay. So, for example, I had a oil and gas reservoir. Okay. So this is the seal. This is the reservoir. Okay, and this oil and gas reservoir, for example, was is now depleted. That means this is a depleted reservoir. What does depleted means? That I have drilled wells and I have taken out oil and gas from it. So the pressure has decreased a lot. Okay. So CCS essentially means that now I captured the carbon dioxide from the industrial site and push it back into the reservoir. Okay. I push it back into the reservoir, I push it back into a geological formation so that it stays there for very long time and it's kind of isolated. So why do I do that? Because I want to sequestrate carbon dioxide, of course. Okay, this process is also called carbon sequestration. Okay, sequestration is another way of saying it because I want to isolate carbon dioxide, right? Isolate CO2 from atmosphere, yeah, for a very long time, maybe 10,000 years or so. This particular reservoir is capable of holding that CO2 into it. Okay, so the technology which are used to actually capture carbon dioxide at an industrial site and then store it in a geological formation, push it back into a geological formation. This process is called carbon capture and storage, CCS, or carbon sequestration. Okay. Now, of course, there is something called CCUS, and CCUS, that you can see that there is an extra U added to my connotation, and this U stands for, of course, utilization, as we said. So, what does that mean? That, for example, what we are doing here, we are taking the carbon dioxide, we are storing the carbon dioxide, but we are not essentially using the carbon dioxide for any of our benefit, right? We are simply isolating it from the atmosphere and then pushing it back inside the ground, right? But we are not essentially utilizing it for any of our purposes. So if with CCS, I mean with carbon capture and storage, there is a process involved where we can also utilize carbon dioxide for our benefit. Those sort of technology is called CCUS, okay? Carbon capture, utilization and storage. Okay. I hope the context is clear for you. Now, why do I need, of course, to think about CCS? This is a known diagram for you. So what you are seeing here, that this is from 1964 to 2012. Actually, I can increase this diagram even, maybe another 100 years. What I am observing, that this is the demand of different fossil fuels, right? Different energy sources, okay? So this is the demand of oil, then the demand of coal, natural gas. Okay, and as you can see, grossly they are keep on increasing, right? They are keep on increasing. So this is the total amount of energy that you will require to be consumed. Okay, maybe at 2012, as you can see, out of which, like almost 90% is coming from fossil fuels, right? Almost, or actually more than 90% is coming from fossil fuels, right? The contribution from nuclear, hydroelectricity, or renewable is considerably lower than what we are consuming with respect to the fossil fuels, right? And that is going to stay for some years, as we said, that we are going through a energy transition where fossil fuel, through the gas economy, going towards the renewable economy. But then the moral of the story is, for next 100 years, we are not going to get completely devoid of fossil fuel consumption. So if we keep on burning fossil fuel, of course, as a byproduct, what we are going to do, we are going to emit carbon dioxide in the atmosphere, right? We are going to emit carbon dioxide in the atmosphere, and that is not something we want, right? So we need to think seriously how to get rid of this carbon dioxide. Now, what is the scenario of carbon dioxide? This is the historical emission of carbon dioxide from different sources. Okay. I'm sorry for that. Historical emission. My apologies. I need to go to the other side. Right. The historical CO2 emissions from different sources. So this is from solids that includes coal, right? Then this is liquid, that means oil. This is from the gases, natural gases. This is from little bit of small flaring, and then from the cement industry. And this is the total carbon dioxide which is being emitted, right? Now look at this. We don't have any record maybe before 1815, okay, 1880, okay. And then look at, this was steadily increasing the carbon dioxide emission. From 1945, of course, there is a steady jump of carbon dioxide emission. 2010, it's even steeper, right? Now, this is coinciding with industrial revolution, okay? Okay. This is coinciding with industrial revolution. So that means, you know, as we have started using these fossil fuels, and as our mind, as our, you know, all over the world, as our life has been becoming more or more dependent on machines, which needs fossil fuels to be burned, we also see a considerable peak in terms of carbon dioxide emission, right? And this is keep on increasing. This decrease, maybe there was a little notch during the COVID 19 situation when we did not do much. There was a little bit of a dip, but in general, this is pretty much uncontrollable. The amount of carbon dioxide that is increasing in the atmosphere is really, really worrisome. Okay, so, and that has something really to do with our lifestyle, right? How we have been exploiting these fossil fuels in a very unsustainable way. So one of the major targets for very many different governments around the world, and hence these famous protocols have been signed. Like one of them, can you name few of the protocols which have been signed in terms of the uh, environmental protection? Do you know some of the names, students? They are very famous. Do you know some of the names? Anyone? Hello, are you there? Anyone can name any of the protocols which have been signed? No, no, those are the, I mean, the protocols, in the sense, you you must have heard about the Montreal Protocol, Kyoto Protocol. The more famous one was Kyoto Protocol, exactly. So, and then the one that was signed in Paris, where Prime Minister Modi also took part, right? So, yeah. So, what these different countries are thinking in terms that, uh, I mean, most of the countries are thinking that they have to essentially reduce the carbon footprint, as they say, the carbon footprint. So this is another way of looking at how the carbon dioxide emission is going on. Now, there is one scenario, of course, that you have to essentially, and if we don't do anything, it will keep on increasing like this, right? It will keep on increasing like this. Now, it's like 1 billion ton of carbon dioxide uh, per year. Okay, so one wage, I mean these particular wages, these wages, yeah, is equivalent to 25 billion tons over 50 years, right? Now, this is where it can go if we don't do anything, right? Even more, maybe, if we are accelerating. So, what is the target for different countries which has signed these environment-friendly protocols? Are to actually, decrease. So, one of the targets is, of course, is to stay where we are. Not only that, develop technology. So from 2006 to 2015, 56 is like the idea is stay where we are. We don't allow more carbon dioxide to be emitted in the atmosphere. And with more research and technology, from 2056 onwards, we want to bring it even down. Right? We also want to bring it down. So, how do we make sure? Because we are essentially developing, and we have a trend which is showing us that the emission of carbon dioxide will increase, right? So, how do we make sure that we are not here, but we are here at 2056? So, what are the measures that we can take to actually, decrease the carbon dioxide emission down from 14 billion tons per year to something like 7 billion tons per year, almost half, by 2056. So there are different processes you can do. Okay? For example, end user efficiency and conversion, end user efficiency and conservation, agriculture and forestry, alternate energy resources, okay, carbon capture and storage. So this is another. So this is our main theme of discussion today, and power generation in a sustainable way. Okay. So this actually says these are the options to reduce the carbon dioxide emissions. Okay. Uh, you can find this particular will that people have brainstormed and put together from Google itself, where it shows the different processes by which you can actually decrease down carbon dioxide. Okay, so if I read a few for you, say for example, of course, agriculture and forestry, expand conservation to 100 percentile. Yeah, stop all deforestation. So these are some of the measures, right? So then cut electricity use in homes, offices, and stores by 25%. So that is kind of in the end user efficiency and conservation bucket, right? Then power generation, raise efficiency at 1500 large coal-fired plants from 4 to 60%. Okay, so that means you burn more coal, but then you reduce the carbon dioxide as well. Okay, so replace coal-fired power plant with gas-fired power plant like this. So these are the different measures by which you can actually bring the amount of carbon dioxide down from 14 to 7 by 2056. So 14 where it will go, and if we don't do anything, but if we do these things, people have modeled. If we do these things, the ones that I have just described in this beautiful wheel, okay. For example, agriculture and forestry, end user efficiency and conservation, power, smart power generation, carbon capture and storage, alternate energy resources. We should be able to. People have demonstrated that we should be able to bring it down from 2000, 14 to 7, right? So this is another way of looking at it. So This is where billion tons per year. So by 2056, if we want to even, keep it down, uh, these are the different fractions that would contribute. So we can see the major contribution will come from electricity and end use efficiency. Okay, so you have to make sure that whenever you are standing on the traffic light, you have to switch off your car. If you are leaving your office, you have to switch off your air conditioning, and so on and so forth. These are smart uses, and everywhere, if we can reduce 25% of power consumption, of course, they're going to contribute a lot. Okay, but then you can see a wage coming from the end user efficiency, passenger vehicle efficiency, other transport efficiency, renewables, of course, and then there is a large amount of contribution that is postulated from carbon capture and storage. Okay, there is a large amount which is still which can be achieved by carbon capture and storage. Now remember, carbon capture and storage is not something that is done in a commercial level today, okay, anywhere in the world. Nowhere it is done. It is only done as demonstration projects. Okay, so there are few demonstration projects in Australia, um, which is, people are starting to plan only. There was one demonstration project where I also worked during my time period in Shell, which was in the UK. The name of the project was, you can search in Google, called Golden Eye Scottish Power's carbon capture and storage project. Okay, so, and there are some in Norway and the Netherlands, but all of them are in the demonstration phase. Okay, so there is another big act in India coming up in next 20-25 years. Maybe we will also have our first demonstration project for carbon capture and storage here back in India. So I sent you, you remember at the very beginning, I sent you one of my papers, one of my publications, where I discuss essentially what are the different scenarios of carbon capture and storage in India, how viable it is, what are the difficulties that India can face, so on and so forth. So I urge you to read that paper. It's a fairly comprehensive paper, review paper though, which discusses about different options on carbon capture and storage which are relevant for Indian economy. I sent you that paper before. Please search my older emails. Okay. Now this is what happens in carbon capture and storage, of course. So this is a CO2 source. This could be, for example, it can be a power plant. Of course, the coal-fire power plant will emit more CO2, right? And then the CO2 is actually is not, what do you see in a normal power plant? If you go there, you will see that there are large chimneys, and from those chimneys, there's black smoke being emitted constantly out, right? And the people around who lives in that area has complaints of coughs and constant coughing. The air is heavy. There is immediate the air is warm as well. There is immediate effect of your air pollution because of these power plant stations. Okay, it's because these chimneys are constantly emitting carbon dioxide and other toxic gases, of course, carbon monoxide, sulfur dioxide, and everything, from these coal power stations. Okay, so the first step is, of course, a carbon capture. You have captured the carbon dioxide. Okay, then there is something called carbon dioxide compression unit. What do you do in the carbon dioxide compression unit? Because when you actually pump it inside the ground, you don't pump it in the form of gas. So you essentially put a lot of pressure in the carbon dioxide, and you make liquid carbon dioxide out of it. Okay, you make liquid carbon dioxide out of it. So the pressurized carbon dioxide, and you make liquid carbon dioxide out of it. Simply like the same process by which you make Coca-Cola, right? So there is a compression unit where you decrease the volume of the carbon dioxide which is produced, and then the carbon dioxide is transported by pipelines. Okay, and then this power plant might not be very close to the place where there is a depleted reservoir, right? Where you can actually store carbon dioxide, right? And then, like we have talked about in petroleum geology, what did we do in petroleum geology by drilling a well? The flow was from inside out, right? The flow was from inside out. The oil and gas was coming out from the underground to the surface. But in this particular case, the flow is outside from inside, right? From outside to the inside. Okay. So the liquid carbon dioxide which you make in the compression unit is directly injected inside the reservoir. Okay. So here you can see, like you have injected water to maintain pressure of the reservoir. Similarly, in this particular case, you are injecting carbon dioxide inside the ground. Okay, and that carbon dioxide will stay there. It is hoped that it will stay there. The gas or the oil which it was there. I mean, so there is a space, there is a void in which the carbon dioxide can nicely fit and can stay there. And by that process, you will emit the carbon dioxide from, sorry, omit the emission of carbon dioxide from the atmosphere, right? This is the whole concept. So this is the phase diagram for carbon dioxide, of course. Okay, so you can see here that yeah. So this is the pressure temperature field. This is the pressure temperature field where carbon dioxide is gas. Okay, and then this is the pressure temperature field where carbon dioxide is liquid, and this is the pressure temperature field where carbon dioxide is supercritical fluid. Okay, so there are both processes. What people are thinking, whether we can inject carbon dioxide as a liquid or whether we should inject it as a supercritical fluid. Yeah, there is no right or wrong answer, but these are the preferred options by which you actually inject carbon dioxide inside the ground. It's never in the gas phase because it has a lot of volume to be covered. Okay, so what do you essentially do? You treat carbon dioxide with certain pressure and temperature so that you reach the liquid phase or the supercritical phase, and in that phase you essentially inject it, right? So now you can see it doesn't have a lot of sensitivity with respect to temperature. Yeah, it can, the gaseous phase, all these three phases can actually stay in all the temperature. Only the solid phase is actually vanished after 350 degree. Okay, and rest of it, all the four phases can actually stay. So it's essentially, increasing the confining pressure. Okay, so increasing the confining pressure, and at a lower temperature, if you increase the confining pressure, you create liquid. At a higher temperature, if you increase the confining pressure, you create supercritical fluid. Okay, and then this is the critical point where all three of them can coexist, right? And this is a triple point where solid, liquid, and gas coexist. Here, liquid, supercritical fluid, and gas can coexist, right? So the more important thing is essentially pressurizing the carbon dioxide, because temperature sensitivity is not that much with respect to its phase change, right? So where do you store carbon dioxide underground? You can store it inside an aquifer. It's a reservoir, but which contains carbon dioxide. Sorry, which contains water, right? So if an aquifer which is not potable, where you don't take your drinking water out from, okay, that is where maybe you can store carbon dioxide. Depleted oil and gas reservoir, that is what we just talked. You can store it in a coal bed. Okay, so of course. So the coal bed has some sort of gas which is CH4, which we call as coal bed methane, and C or CSG, coal seam gas, which we just discussed in the last class. Okay, so when the CH4 is out from the coal, then perhaps that coal bed is also a good candidate for carbon capture and storage, right? You can also store it in fractured basalt, because you like a normal reservoir which needs porosity and permeability. Okay, the reservoir where you also want to store carbon dioxide, that would also require porosity and permeability, right? Because in one case, what you are doing, you are trying to extract the liquid or the gas from the reservoir, so it has to flow. In this particular case, what you are trying to inject carbon dioxide either in the supercritical fluid phase or in the liquid phase inside the ground. And there also the liquid carbon dioxide or the supercritical carbon dioxide has to flow. You cannot just you cannot just dump it in the well. It has to flow inside the reservoir. So it needs porosity and permeability, right? So hence we are targeting these aquifers, depleted oil and gas reservoirs, coal beds, or fractured basalt because they have their intrinsic porosity and permeability. For example, fractured basalt doesn't have a lot of intrinsic porosity, but then it has or permeability. I mean, primary porosity or primary permeability, but it has fractured permeability, right? Because it is fractured, right? So there also maybe you can store CO2. So, but then you remember all these things are right now under research, and it's the governments and everything, everyone, all the top agencies are putting a lot of money around carbon capture and storage. So this is one of the key areas where people are doing a lot of research, and there is a lot of money to support that research as well. So uh, it's just reverse engineering. In oil and gas, you had to think that you had to take things out, and in CCS you have to put things back, inside the ground. So that sort of, but the basic uh, technologies and the basic knowledges that you require uh, for CCS is very similar to what you need for oil and gas industry, right? Which we have already discussed in our coal geology as well as petroleum geology classes. Okay. So the important thing is containment is the key. What does containment mean? That the carbon dioxide that I have put inside the ground, okay, that need to be staying there for maybe at least 10,000 years. Next 10,000 years, you have to prove that the carbon dioxide will not come out of the ground. Okay. So there is, for every government there is some sort of rule about the containment years that you have to prove. For some government, maybe 10,000 years. For some government, 5,000 years. Maybe 1,000 years. Who knows? You have to prove that the carbon dioxide will not come out in the very near future. Yeah, and that you have to do by showing some modeling that and understanding the overall geology of the reservoir. That yes, it can contain. So first thing, and is there enough storage? I mean, if is the reservoir small enough, or is the reservoir large enough that it can contain enough amount of carbon dioxide that I want to store, right? So it needs to have GRV, that is gross rock volume, enough porosity, enough permeability. Okay, like similarly, the way we have been calculating UR, ultimate recovery, here you are calculating is there enough storage? I mean, yeah. So whether that has enough gross rock volume, enough porosity, enough permeability in the reservoir where you want to actually you aspire to contain carbon dioxide. Okay, are there chances for top seal failure? Okay, the seal whatever is there, which is a shelly rock, if while I inject carbon dioxide, will the seal fail? Will the seal get fractured? That's another risk. Okay, whether there are chances for shear failure, that means whether there will be faulted, whether there will be chemical reactions. What sort of chemical reactions if we are pushing, for example, liquid carbon dioxide or supercritical carbon dioxide? Is there any chances for contamination? Okay, the carbon dioxide that we are putting, will it contaminate maybe the water that we want to take out from the underground? Are there gas chimneys? So gas chimneys are some features like you can see them in seismic. For example, this is a typical picture of a gas chimney. So what a gas chimney is? Gas chimney is a geological feature. So this was a reservoir, and then there were leak paths, maybe faults or fractured zones which we call gas chimneys, okay, through which the oil and gas, whatever was there, has simply escaped to the ground. Now, I don't want to push carbon dioxide in such a reservoir where there is an existing gas chimney. Okay, geologically there is a existing gas chimney in the subsurface, right? That is not a place where I would like to push my carbon dioxide into, right? Simply because this has inherent risk of carbon dioxide leaking, because there is geological proof that the oil and gas which was here has actually leaked through this gas chimney, right? So if in a reservoir, if we find there is already a gas chimney, I would not perhaps advise the company to actually push carbon dioxide back into the same reservoir, right? So here is another picture of a gas chimney. Okay, so you can see here how carbon dioxide has escaped, and this has completely disturbed the character of the seismic, right? You can see this beautiful anticline which could form a trap, yeah, which could actually form a trap, yeah, and where oil and gas could have been, or when the oil and gas was not there, we could have actually pushed carbon dioxide into. But then what you can see that along around this zone, the character of the seismic is really, really wobbly. That beautiful continuity of the reflectors are no more there. Okay, so what does that mean? That this typically happens when a gas chimney is there. So this essentially proves that the oil and gas, whatever was there in this trap, has escaped through this gas chimney. Okay, so it is not recommended to actually push carbon dioxide back, right? Now, of course, this carbon capture and storage would be possible when the carbon credit system is in place. And we talked about carbon credit system a bit in the last class, but let us take you through another time. So, a carbon credit is a generic term for any tradable certificate or permit representing the right to emit 1 ton of carbon dioxide or the mass of another greenhouse gas with a carbon dioxide equivalent TCO2e equivalent to 1 ton of carbon dioxide. So it's like you have to pay to emit 1 ton of carbon dioxide, right? And this is going to be so expensive. So say for example, I'm an entrepreneur, and then I want to establish a company, right? And then tomorrow that company is an industry. Maybe I want to establish a power station, okay? And then I know that this is the amount of carbon dioxide I will be burning every day. Okay, this is my modeling shows this is the amount of carbon dioxide I'll be modeling every day. So what I have to do to actually emit that carbon dioxide, I have to pay that money to the government. That see, I'm emitting the carbon dioxide. That means I have to pay you this much amount of money. Now that I can do. The other thing that I can do, I don't pay the government, but I take care of the carbon dioxide. What do I do? I actually sequestrate the carbon dioxide. I actually put the carbon dioxide back in the ground, right? So that will perhaps be less expensive than to pay the government, because the carbon credit system is going to be extremely high. Okay, so you have to actually pay a lot to emit carbon dioxide into the atmosphere, and this is where you know the global economy is heading towards. So we are heading towards a transition of gas economy and then to a renewable energy economy, and in between, of course, such carbon credit will be in place. Australia is supposed to be implementing carbon credit for the first time, and I can tell you this very frankly, this is not very far away when this will be a very known thing for people all over the world. So if you want to emit carbon dioxide, you have to pay to the government, as if you have to buy the license to emit carbon dioxide. Now that is going to be expensive. What is your alternative to avoid that cost? You can invest in CCS, carbon capture and storage, because you will anyway emit carbon dioxide, right? So carbon credits and carbon markets are a component of national and international attempts to mitigate the growth in concentrations of greenhouse gases. I hope you understood what it means. One carbon credit is equal to 1 ton of carbon dioxide, or in some markets, carbon dioxide equivalent gases, both greenhouse gases. Carbon trading is an application of emissions trading approach, right? So that's what we just explained. The goal is to allow market mechanisms to drive industrial and commercial processes in the direction of low emission, less carbon intensive approaches than those used when there is no cost to emitting carbon dioxide and other greenhouse gases into the atmosphere. Because nowadays, if I have a plant, you know, I mean, if I can emit as much as carbon dioxide as I want, I just have to have a simple, permit from the pollution control board, and that's it. Who knows how much carbon dioxide am I putting into the atmosphere? There is no regulations, and that is where the carbon credit will actually play a big role. Okay. So there is a big debate around CCS, carbon capture and storage, whether CCS should be the part of the technological mix, where the society is moving towards developing a non-fossil fuel low carbon system. So that's one of the debates that people are putting philosophies around, and there are plenty of works around it. You can search in the internet. It's completely full with these sort of topics. Whether including CCS in the technological mix that is supposed to lessen the fossil fuels impacts will bog us down even deeper. Will CCS technologies simply deepen the current carbon and fossil fuel lock-in, or does this inclusion in a mix allow a breathing space whilst the longer term transition to the new low carbon pathway is engineered? Okay, that's what we just discussed. Okay, if I give you a nutshell in India, what is the scenario in India? The initiation of CCS venture largely depends on the success of the techniques in these industrialized nations. So the first world countries have to show the path. Then perhaps you know uh, India will take it seriously. CCS is not expected to be applied in India before 2030. Of course not. A reliable storage capacity assessment is a primary necessary, and I can tell you now that there is a call from the Indian government, okay, to actually submit projects from different universities and science research institutes to actually do the same thing. A reliable storage capacity assessment. That is currently is being done. An initiative has been taken up by Prime Minister Modi, and there was a big science. I don't know if you know about the science congress or the conference that took place, named as Vaibhav, and there was a big session dedicated just for carbon capture and storage in India. Okay, so Indian government is well aware of the fact that CCS is going to play a big role in near future, and um, of course, it's not going to happen very soon. It's in the research stage. People are putting more, you know, what should I say, more consolidated effort around the projects in CCS, but it will happen in very near future, of course. So, based on rigorous scientific assessments of storage sites and volume, an optimization model should be applied to identify cost-effective sites for CCS power plant, remembering the constraints like electricity, coal, the separated CO2 emissions, and even the cooling water. There exists economic barriers for developing countries like India, of course, in implementing CCS technology because it is expensive, even in the carbon credit system in place. Okay, That is something you have to remember. The way carbon credit system can be applied in a country like Australia or America or in the Europe, where especially Western Europe, where the economy is better than us. I'm sure they can afford it, but then for us it's little bit tricky. But we are getting into the right direction, of course, approaching the right direction. The total emissions per unit of produced electricity are notably reduced. This puts doubt on the benefits of the huge investment for CCS infrastructure deployment in India. Public support would be bare minimum to establish conditions for CCS development in India. I don't want to, I mean, elaborate on that, but you know why. CCS plants will face strong competitions from renewable energies technologies, of course, right? Because in a way, CCS is also kind of supporting the fossil fuel economy a little bit. So that's about it about CCS. What I want to recommend is a paper, which is in my next slide. You can search this paper by Vivan et al. Prospects of carbon capture and storage in India's power sector and integrated assessment. That was published in Applied Energy in 2014, and also the paper that Tandon sir and I wrote, and which I sent it to you. That also provides you with a very good account around the carbon capture and storage scenarios in India. Okay, but I can tell you this is one of the primary research areas where, you know, as an earth and environmental scientist who has knowledge in earth science as well as who has knowledge in environmental science, the ones which are very apt for you guys, who are studying a course of earth and environmental science, not only earth science, but also environmental science, where carbon capture and storage is going to be big in near future. And I think it's one of the areas, if you choose to do your research, if you choose to do your make your career, it's going to look extremely lucrative for future. Okay, of course, if you have interest, but mm, this is going to be big. So, and this fits to your portfolio, like you have been studying a little bit of earth science, a little bit of environmental science, and this is a perfect subject where both your skills would be extremely beneficial and complementary. Okay, so that's where I want to end. If you have any questions, I'll be glad to answer. Any question? Not interesting enough? Yes, that's a good question, Meenakshi. Yes, enhanced oil recovery is also uses carbon injection methods, but then of course the amount of carbon dioxide which is pushed in your things is not the scale is very different. Is little carbon dioxide compared to the CCS what we are talking about. Here the main aim is to push carbon dioxide into inside, right? In your main aim is to take the oil out, but the process is fairly similar. Yeah, scale is different. Anything else? Okay, if not, then I will talk about clathrates tomorrow. Clathrates, or what we call as gas hydrates, and then I will send you the uh, quiz question paper. Okay, after the class tomorrow. All right, then I'll sign off now. Thank you. If you have a question later on, if you think you want to understand more, please read the papers that I have just suggested. And if you want to discuss further, I'm always happy to do so. Thank you.